Hey y'all, this video is going to be introducing Coulomb's law, which is basically it's an equation that gives a measurement of the force produced by electrons and protons and charged particles. And so we're going to break it down, explain it, and in another video, we'll be giving some worked examples. So let's start out. Okay. So first, what I want to do is discuss particles in general or objects that are charged. So I can have, say, a couple objects, and we're talking about two objects here because Newton's three laws still apply in terms of forces in F equals ma. The sum of the forces equals the mass times the acceleration. His first law, which is the law of inertia, or the idea that objects aren't changing if there are no unbalanced forces in terms of their motion. Then his third law, which basically says we have equal and opposite forces on objects that interact. And here we have objects that are interacting, and these objects aren't interacting with gravity, but they are interacting with the electrostatic force. Okay. And so if we have, say, a negative particle and a negative particle, or a negative object and a negative object, could be many electrons added on to one object, could be none or one, but it has to have a net negative charge, meaning there have to be more electrons than protons. Remember, all atoms to start out with in the void, typically we consider to be neutral, or we would consider a standard atom to be neutral. So here we have two negatives, and what are they going to do to each other? They're going to be near each other, and there's this force that's between them. We have some field lines, which we'll discuss later. We have two negatives near each other, and we want to know, and there's more going on here, but two negatives near each other, and we want to know what type of force they exert on each other. And what we're going to see is that this one will have a force pushing it that way from this one on the right. This one will have a force pushing it this way. They will repel because we have a negative and a negative, and they're going to repel, meaning the force is going to be in this direction on one of them and this direction on the other. Okay, and so we're going to wonder about the size of that force, maybe the direction, but ultimately we also have to consider the distance here between them, and we'll call that distance r. Okay, the reason we might call it r, it's certainly a displacement vector here, or a position vector rather, displacement. But what we have is that this object might be orbiting around the other one, or we might use that analogy when we're talking about gravity. And so, for that description, and so when it's orbiting around, that would be the radius of its orbit. Now, here we just consider it to be a distance, and we'll just label it with r. In addition to that, this object has a charge. We'll call that charge Q1 for the charge Q on object 1. And this one we'll call Q2. It'll have a charge of Q2. It's very similar to objects having masses. So if we think about an analogous situation, I'm going to use this in purple here. Recall, for the law of universal gravitation, we have big G m1, m2 over r squared, where we have some mass m1, we have some mass m2, we have some distance between them of r, and we have the forces on these objects pulling them inward like this. And gravity is an inward, it pulls inward, it just pulls, it doesn't push. And so we have two objects that have masses here that are pulling inward, that have some distance between them. Here we have two charges that are either repelling or attracting, depending on the situation. For example, I could also have this situation where I have a positive and a negative, and the forces are pulling them inward, and they are still a distance r apart with charges q1 and q2. So I could have these two different situations where I have a plus and a minus, and those would attract. And this reminds me very much of this situation over here with gravity. So it turns out that because we have these attractive and repulsive forces, the formula is going to actually look very much the same. So let's see an example of the equation. Let's break down this equation, or break down this idea. So the first thing I want you to remember to think about is how do we have two objects? Let's say we have two magnets. When they come close together, what exactly is happening? So here's an aside number 2, thought. For magnets, when we bring them close together, we feel a really strong force. But when they're further apart, the force gets much weaker. When they're further away, it seems like it's way weaker. Like you don't feel the magnet until it gets really close and clicks onto something. So we get a strong force close in, and then we get a weak force far away. And certainly it gets weaker far away, but it gets way weaker far away. So if we have two magnets over here, and they're, say, distance big r apart, we have this weak force. Okay. And so it turns out that because electrostatics, or electrons and protons, that charge stuff, is highly related to magnets, it follows a very similar rule. It follows this inverse square type of relationship. And so I'm going to start out by saying that Coulomb's law, and let's use black here. Coulomb's law itself talks about the force, and we'll say electrostatic. We'll have for now an electrostatic in the subscript, is related to the size of my two charges divided by that distance squared, r squared, this r value over here. And then instead of g, like we have with gravitation, we have another value, k. And with gravitation, I'm just going to remind us, g equals 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. That's the unit. And we want to know why. Well, this is actually a really small number. And recall when I was talking about gravitation, I said, hey, I can resist the force of a full planet just by jumping. So I, this little human, can resist this really weak force of gravity. This small number indicates that gravity is weak. W-E-A-K. Gravity is weak. And this number describes how weak it is. Whereas with electrostatics, everything in your body is held together by these types of forces. And as a result, this K value, which tells us the strength of an object or of an interaction, this K value is really kind of big. We're going to say 9.0 times 10 to the 9th. And again, we want to get the right units. And so it's going to be Newton meters squared over coulombs squared. Okay, where charge is in coulombs. And so the charges will cancel out, the meters will cancel out, and then we'll be left with newtons. And so 9.0 times 10 to the 9th, that's 9 billion. So this is 9 billion, and this is like 1 over 10, 1 over 100 billion or something like that. So this is a very small number. This is a very big number. Electrostatic force is 20 orders of magnitude bigger than gravitational force. It's like saying, okay, well, for the same distance away and the same stuff in the numerator, you'd get a force that's not, that's not a billion times stronger. It's not a trillion times stronger. It's not a quadrillion or a quintillion times stronger. It's, like 100 quintillion times stronger. It's a ridiculous difference in strength between these two forces. And so this equation describes the force between two charged particles. So how much are electrons attracted to protons? How much are they repelled by other electrons? And that's responsible for all this fancy chemistry stuff and physical interaction that you see on a daily basis. It's responsible for friction. It's responsible for all sorts of other phenomena. And to some extent, it's also responsible for all the fancy electronics you have today. And keep in mind that this constant here, this 9 billion, is something that's been measured experimentally. And we have a good deal of precision for that over the past century or two. And so that's sort of my description of this rule. As the charges get bigger, the force gets bigger. As the distance increases, the force gets smaller. And any combination of those will affect it in a particular way. So keep in mind that this force, electrostatic, is proportional to 1 over the radius squared. So that means that we have an inverse square law here, just like we have with gravity. So the same types of things we can expect with it, except for the fact that this force will be signed. It will be either negative or a positive, depending on whether we are attracting or repelling. Because instead of Q1 and Q2 being negative or being only positive, like masses are, Q1 could be negative and Q2 could be positive. That would give me a negative force value, and that would indicate this kind of attraction. At least in the context of this, what we're talking about here. So this is a little bit of a view on Coulomb's law. Hopefully it's going to help you conceptualize problems. And we'll move on in the next video to solving a problem with Coulomb's law and looking at a few different variants. Okay, have a great day.